Hopefully my mic works. I'm given this, I would say, not so easy task to entertain you in the last hour of today. It has been a long day. I'm sure it was very exciting, and you learned a lot of things. And not even being the last speaker, but I'm supposed to now, extend what George and Roshan was talking about to another type of systems, right? So when I was thinking about how I'm going to handle it, I thought, well, I need to motivate this with some examples at the beginning. And then I looked back, what was the simplest example of time delay systems I kind of ever dealt with, or maybe if not the simplest, but one of the first. Okay? And then this is a very classical example. If you are control engineers, there's almost impossible you never seen this problem. Okay? And this is called stick balancing. Okay? So it's a simple system. It's actually a 2-degree of freedom mechanical system where you model this stick in a plane, and you want to make sure it's standing up there. Okay? It's a classical problem. You can actually derive the equation of motion. There are 2 second-order differential equations. They are actually already nonlinear, so that may think that this is make your life a little more complicated. It luckily has a nice simplification. So as a matter of fact, if you stare at these equations for a while, you can realize that you can actually eliminate the x coordinate, and you come down to a single equation, right, which is a second-order nonlinear differential equation. Okay, and then frankly, when you start to learn anything about control design, you always start with linear systems, right? So if you're thinking about how to balance this pendulum, you would definitely just first say, what if phi is small, and I could just get rid of all these nonlinear terms. And indeed, if you do that, then your life gets much, much simpler, and you just got a second-order differential equation with a single control input. Okay? So we teach it actually for our undergrads, right? So this is a problem which we often show. And that's how we kind of start to talk about, for example, stability, because this has a nice feeling about, indeed, if I don't do any control, then I get this simple differential equation, and I calculate the corresponding characteristic roots, or sometimes we call them eigenvalues. And it turns out that one of them is on the right half-complex plane, so this is an unstable system, right? And it's a very nice problem, because indeed you can physically see that the pendulum would fall. Okay? And then typically we teach PD control, or you can also look at it as like a linear state feedback control. And then we basically plug it back to the system, and we analyze with the students and say, okay, so in this case, how does this stability change? So again, you go through your characteristic equation, and you learn your standard Rouse-Hurwitz criteria. And then basically you figure out that there is a combination of control gains when I can stabilize the system. Of course, at the linear level, right? And it's a very simple solution. You basically learn that your P gain is going to be larger than your weight. Okay? And you also learn that your D gain has to be positive. Okay? So it really seems very simple. But if you really try to do this problem, okay, yourself as a human, then you quickly learn it's not that simple. Okay? And then, as a matter of fact, there has been many experiments done on this. And it turns out that one of the reasons is because when I'm trying to balance a stick, I have a delay in my control system, right? My eye is looking at that stick and trying to measure the angle and trying to measure the angular velocity. And then that signal has to go to my brain, right? My brain is going to process it and sends down on the motor neurons to my fingertip. And it does take time. Okay? So if you take this into account, then your system changes a little bit. Okay? And again, I'm still at the linear level. And what happens is that your characteristic equation, or your equation, becomes a little more complex with these time delay terms. Right? So you can see now that the control force is actually going to be depending on the delayed value of the value of the state and the derivative of the angle. Okay? And if you go through your characteristic equation, then suddenly something really weird happens, right? So previously, I had this second-order equation. I can actually solve it with high school logic. suddenly here you try to solve it, and turns out that you don't have like 1, 2, or 3, but you actually have infinitely many solutions, right? So that single delay, that single parameter, made something much more complex, okay? And it turns out that in this simple system, you can still actually figure out that, what is the stability boundary. So it turns out that it's still true that your P gain has to be larger than the weight, but it's also going to be an upper limit on it. And if you try to balance a pendulum, you can quickly learn that if you try to use too high gains, then you would be actually in trouble. And what really happens if you draw it as like a stability chart is that previously, when you had no delay, this entire domain here in the PD plane was actually stable, okay? Once you start to increase the delay, this domain gets shorter and shorter, okay? And there are two types of stability loss. So as a matter of fact, this straight line still stays here. It simply means that I didn't give enough gain to the system. The pendulum is just going to fall off, okay? And if you have too large gains, then what happens is that you kind of push through this dynamic stability loss, right? So you have two complex conjugate eigenvalues which move to the right half complex plane. And then you start to see oscillations, okay? So again, this is a very classical problem. And then people also thought about, well, what happens if I start to increase my delay? Is there a limit to this? And in this figure, you can already see this tau 3 is such that I don't have any stable domain, okay? So for example, let's say you drink a couple of glass of wine, right? Then typically your time delay goes up. If you try to balance in that case, you're probably going to fail because simply the delay is going to be too large, okay? And there's a very simple formula to calculate how large this delay is. So once you go through the algebra, and there are two papers here, which is actually not by me, but by Professor Stepan and Professor Inchberger in Budapest, they actually calculated that, well, it's really just proportional to the square root of the length of the pendulum. And then you can actually calculate how large this delay is. So for example, you can measure a reaction time. There are many different ways to do that. And you quickly learn that this is roughly about 30 centimeters, which is about 1 foot if you are from America. And then and 1 ruler if you are an engineer, okay? So that's what you can do. So you will be able to balance, for example, let's say a broomstick on your fingertip, but you won't be able to do a pencil, okay? Now, if you really get excited about it and I say, well, can I still do a pencil? As a matter of fact, you can do that, but you have to use your chin, okay? Because the delay between your eye and your brain is actually smaller, and that actually allows you to do that. And it takes some practice, I have to tell you, but some people are capable of doing that. And you can try at home if you have a golf club or a broomstick. Actually, you can even do it on your foot, okay? Again, it's a little practice, but it works. Now, you might say, well, this is a little bit of a silly example, right? Where does it come into any industrial applications? So a few years ago, they made an interview with, maybe I'm a little delayed here, okay. Made an interview with Jeff Bezos, right, who is definitely more rich than I am. And he was trying to explain, this is actually a very important problem in the current industry. So let me see what he said. And I have to.
Doing a vertical landing is an inverted pendulum problem. So you're balancing a pencil or a broomstick right on the end of your finger. And actually, this is one. Rockets love to be big in a bunch of ways. There's a lot of advantages. One big disadvantage to a large rocket is manufacturing is difficult. Right. But there are a lot of advantages to a large rocket. Parasitic mass doesn't matter as much. Rotating machines like to be big because they have parasitic losses too. Right. A lot of advantages. Vertical landing likes big rockets because it's easier to balance on a broomstick. You can balance on the tip of your finger. Try doing that with a pencil or a toothpick. Right. You can't do it. And the reason is that the inertia slows everything down. So it's much easier with something that has high inertia to balance.
Okay, so he's saying that if you want to balance a rocket, that's much easier. You need a couple of $1 billion to build that, but as a control problem, it's actually easier to balance a bigger rocket than a smaller rocket, okay? I wanted to use this as a motivation that indeed time delays make things sometimes not necessary as we expect, and indeed it do come up with real engineering applications, okay? Another field where it comes up a lot is actually automated vehicles, right? So indeed, in the last, I would say, 10 years, there has been a huge development on this field. And indeed, as you drive cars yourself or riding with someone, you know that it matters how fast those cars are reacting, right? It can be life and death. And actually, this is also another nice application of time delay systems. So for example, if you look at, I would say, the simplest possible model of an automobile, which we call the kinematic bicycle model, it's only 3 equations. We are modeling the position of the rear axle center point, and we're modeling the orientation of the vehicle. And again, you try something very simple. You try to have a control law, which essentially a linear control law, right? I did this little trick to get rid of the tangent function. And then, again, you can go through the same analysis. And then, not so surprisingly, you start to see very similar equations, right? You start to see these exponential terms, which are going to lead to these infinitely many characteristic exponents. And turns out, in this case, actually what really matters is what we call the non-dimensional delay, right? So your speed matters, right? So how large your delay is, it really matters how fast you go. So that's kind of the critical parameter. And you got something very similar. You see a stability chart where actually it starts to shrink as you increase the delay. In this case, actually, there is no critical delay. But of course, after some certain delay, this becomes very, very small. And we actually showed this experimentally a few years ago in our test track in M-City, where actually the delay was coming from GPS. So the car was getting GPS data too slow. And you can see this stability loss as the vehicle is leaving the lane. OK, so I can also tell you this was actually filmed from a higher location. It was very scary to do the filming. I did it myself. That was probably more scary than sitting in the car and observing this motion. And indeed, auto manufacturers also struggle with this. This is actually a Tesla. And this is one of the autopilots. I think the sound is not so necessary. But you can see in this case that you can see this swaying motion. They don't really increase to infinity, because indeed there are nonlinearities, which at this point are stopping the system. And eventually, it requires the driver to interact. I can tell you Tesla actually solved this problem. So last night, I drove in, or I was driven in with a Tesla Model Y. And it was fully in this FSD mode all along the journey. It was really, really performant. Okay, so we can see that this technology is developing a lot. And now, of course, because this is being deployed, people start to worry, well, what happens if I remove the driver? So for example, in the state of California, it is actually required that every one of these vehicles which are deployed without a driver, they must be remote controllable. Okay? And that's a big issue now, because there are these centers somewhere around the world. The companies are not even telling you well, right? And there is someone sitting there who is looking at all these, for example, Waymo cars driving around. Okay? And then what they need to do is that they need to intervene if there is a problem. Okay? Well, as Roshan showed us, if you try to do an experiment in California while you are sitting in ETH Zurich, well, there is some significant delays there. Okay? So I think it was last year we did a demo in M-City, which demonstrated it extremely well. So what we actually did was we had a real automated vehicle driving on the tarmac. Okay? So on the right, you can actually see that. That's a drone footage. The drone is just following the vehicle. And on the right, if I want to use a trendy word, we used a digital twin of the system. So that basically looks like a computer game. And you can see there is a pilot, which was actually an NSF program manager who was supposed to drive this car. Okay? And then the demo supposed to demonstrate that this works. Okay? Let's see what happened. Okay? So again, one more thing is maybe the reason it's done in this way, because you can put objects on the road in the simulation software which are physically not there, right? So that kind of maintains the safety of the system. But let's see how the guy did.
And after it makes that left turn, it will encounter a stranded vehicle. There it goes. It's being a little cautious. you see the stranded vehicle in front of it. And at this point, the vehicle will slow down, will stop, and phone home for help. It's at this point that Daniel Lenzel is being instructed to put his foot on the brake, hands on the wheel, and the takeover will happen. He's now driving. So he is driving from that building, the vehicle on the facility here, and he's doing so with only the simulation to look at.
So as you can see, it didn't do very well, right? So there are certainly issues, when there are time delays in the system. And then these problems are there in our daily life. Maybe before I talk any more technical, as a final example. So this is actually an example I've been working on for maybe 2.5 decades by now, and I'm showing some of the papers and a book we published on the topic. So we started kind of thinking about in a larger scale traffic problem, right? When we have many, many vehicles, and we try to understand, how they behave and how these congestions are triggered and so on. And then over the years, we actually shifted that, well, if this automation is happening, and it is indeed happening, as I mentioned to you, can we use these automated vehicles in the traffic flow? On one hand, can they benefit from additional information through connectivity? On the other hand, is it possible to kind of use them to control the traffic? Okay? And just to illustrate, how do these so-called phantom jams look like? So this is from a high vantage point, and you can see that how the jam is developing and traveling against the traffic. And then we are in Los Angeles. I don't think I have to kind of promote traffic jams so much. Then it's every day here, basically, in peak time. So if we could actually provide a solution to it to any level, that would be certainly a large benefit. Okay? And as I mentioned, we started to first work on just understanding how humans drive. Okay? So back, let's say, 2 decades ago, there were no automated vehicles driving on the road. So what we did, we built actually a model. And now, finally, I start to talk a little bit more about nonlinearity. So far, I really didn't talk about linear stability. And now you can see this is a nonlinear time delay system. Okay? So indeed, the linear techniques will have limitations in order to describe the system. And the type of nonlinearities we have in our system is typically related to the fact that your vehicle is still limited in torque, right? So even with electric vehicles, you can have limited acceleration and deceleration. For example, does anyone know how large a maximum deceleration of a car is? Anyone? Minus 8 meters per second squared. That's a very good estimate. Yes, a very aggressive one. You understand it that when that happens, then 80% of your weight, okay, is on your seat belt. That hurts. Okay, that seriously hurts when that happens. Okay, so there are limitations like that, and sometimes people also don't want to get to that high level. Another limitation is we still have speed limits. Though I actually learned from the Tesla FSD that they can actually go above the speed limit, so you can deliberately set your car going 80 when the limit is 70. That begs some questions, but still there is some speed limit. So there is another kind of saturation in the system. Okay. So once you model the system, then you start to see something very interesting. You start to see the interaction between the time delay, the fact that you are responding to the vehicle in front of you with a certain delay. And that's, in case of a car, it's typically around 1 second, right? So that's the difference between you seeing something and actually putting a brake torque on your wheels. And then the nonlinearity, that these human models are actually nonlinear. Okay? And then you found something very interesting, what we call a phantom traffic jam. Okay? So if you run, for example, just some simulations or collect some data, what you will see is that sometimes a vehicle makes some braking, but then basically, eventually the system recovers. Okay, so as a control engineer, say, oh, everything is fine here, right? It's a stable system. We don't have to worry about anything. Okay, the equilibrium is stable. However, it turns out that if you don't model the nonlinearities properly and you don't understand, then you will miss that, as a matter of fact, there are two more invariant objects there. One is an unstable unit cycle, which is very difficult to kind of measure. After all, it's unstable, right? But if your perturbation becomes too large, then what happens is that actually you go over the limit, and you start to trigger these traffic jams, and they are actually corresponding to a stable limit cycle in the system. Okay? So now you are definitely reaching that this is something you won't be able to do just by using linear theory, right? A linear theory would either make your equilibrium stable or unstable. And I didn't change any parameter here, right? I only changed the initial condition of the system. So now this what happens for humans, right? So if it's great, we understand, and what is the solution? And of course, when the time we kind of discovered this dynamics, then people are like, oh, you should really educate people how to drive, and so on. I can tell you we miserably failed on that, right? So that didn't work. But there is a hope here, like with all this technology which is coming to the road, maybe again we can use these automated vehicles to guide the human drivers, okay? So, well, the human is still there. We still have the human delays, right? And we also have the nonlinearity. So we didn't take all the human drivers out of the road. I think that's going to take probably a couple of decades, if not more. But we added something where we can design, right? So for the automated vehicle, we can actually design the controller. And indeed, there's going to be some delay here, which we actually have to take into account. So if you look at this as a control problem, even though you have only 3 equations, this is actually a very difficult problem. Okay? It's nonlinear, and you have multiple time delays. So if you try to use some kind of classical methods like the called Lyapunov-Krasovsky techniques, this is hopeless. Basically, you would get integrals that even in this huge screen I would not be able to fit. Okay? And you would basically get super conservative results. So when we were looking at this control problem, and then we started to read what George is doing at ETH, we were like, well, maybe this is something where we can start to use these techniques in order to design controllers for this problem. Now, first, of course, we really wanted to understand whether this is even possible. So my colleague Bence Sachs actually did many experiments. He dragged his whole department to do these experiments and driving and following another vehicle. So I don't know how many glasses of beer he had to pay for that, but eventually he had some fantastic data. And he was able to measure the human reaction time delay. Okay? He could actually identify some of these nonlinearities, which he's actually going to talk about in a poster tomorrow. And he could even, of course, measure the delay of the machine. So the only kind of question remained is how we're going to design this nonlinear controller here, which is potentially nonlinear, right? I mean, the system remains nonlinear even if the controller is linear, but potentially we are thinking about designing nonlinear controllers, okay? So as simple as it looks, it's only 3 equations. This is actually a very hard control problem. Okay. So now I'm going to switch gears a little bit and talk a little bit about SSMs. After all, this is what the session is about. Okay, and we need to understand how to do these reduction in nonlinear time delay systems. Okay, that's kind of the goal. And so let's take a look at maybe a simple setup when we only have 1 delay. Okay, so if I give you this problem, and this is actually what essentially Roshan was already talking about, right? And there's just a delay added here where we have a nonlinear system, and then we need to design this controller. So if someone gives me a controller, I can actually start to look at the closed loop dynamics. And I already kind of started to use that terminology, which you have, if you said in the previous talks, you have seen that I separated the linear part, and I separated the nonlinear part of the system. Okay? So that's basically what kind of happens, because you need to kind of understand first the linear part and calculate those eigenspaces in order to actually construct a SSM in this case. Okay? So, however, when you look at this problem, you still see some kind of asymmetry here. So on the left-hand side, you can see the derivative of the state, right? But on the right-hand side, you can see the state, and you can also see the delay value of the state. So it's not really in that kind of classical form that you have seen, for example, from George and Roshan, where there was like a linear term and the nonlinear term, right? So we have these multiple terms here, which we kind of have to deal with it. And people started to think about it actually, I would say, in the 1950s. I mean, that's when it started to come up. Actually, Bellman in the US worked quite a bit on time delay systems. And then also at that time, on the other side of the Iron Curtain, there were a couple of people like Mishkish and Kolmanovsky. And they came up with the idea is that, well, you're kind of looking at this system not the right way. Okay? When we're saying, like, our state is this X, maybe not the best way to do that. Okay? And they extended this notion. And what they said, well, what if we extend the state with a history? Okay? So rather than just saying, my position is this, I'm going to tell you, this is my position, and I tell you what my position has been in the last tau seconds. Okay? So if you think a little bit more abstractly, then what is really happening here, that rather than just thinking about this hat point evolving in this low-dimensional space, you actually have a string, which is kind of, it's pulling it. And then what you really should do is you should think about how this string is changing its shape. Okay? So that's quite some step up, right? It's like, well, but how does it help me? Okay? Well, it turns out if you do this, then you can actually get that classical form, which we had previously. There will be a state, which is the price we pay that this is something more complex that we had to deal with before. Okay? And then we're going to have a linear term, and we're going to have a nonlinear term. Okay? And instead of matrices, we start to have operators. But there is a nice equivalency between what happening at the linear and the nonlinear level. Sorry, at the ODE case and at the DDE case, right? So it makes the problem harder, but it's still doable. Okay, so these systems are still actually subject to the same mass, and I'm going to show a little bit more about that as we go on. Okay. Any questions before we move? Just to make sure everyone is awake. Yes. Please go ahead.
In one of your slides, like a couple of slides ago, I think measuring the headway between the two cars.
Yeah.
Do we also assume a delay in that measurement as well?
Yes.
In the equation?
Yes, we do. So I go back to this just to kind of make sure.
That h dot t, so there we do not have a delay in that measurement.
Yes.
So what I mean here is that if we have a sensor and that is measuring the state of the human, like assuming that no ground truth is available in the AV from an HD, so we can assume there that VHV t minus tau or something like that. Will that change the overall formulation and the outcome if we also have the h dot t with a delay?
Yeah, that's a very good point. So the way I wrote it here, I wrote the speed of the human driver and the speed of the automated vehicle ahead. In reality, what we typically look at is the relative speed within the two, which is exactly the h dot. Okay, so it's just a different way of writing it, but that's already included in the system, and indeed it's important, right? That also contains the time delay. Okay. Any other questions? Okay, so let's dive in. So I come back to this abstract formalism. Now, to make our life a little simple, let's take a look at this problem on the linear level first. Okay. So if you look at the linear level, so basically you throw away the nonlinear terms, then actually many of the classical techniques you can try to use. So you can try to use exponential solutions, and then you start to get the characteristic matrix, and then you also got the characteristic equation. And as we discussed, this has infinitely many roots. Okay, you typically can't solve them in a closed form fashion. In terms, what you get lucky is that these roots tend to be kind of accumulated toward negative infinity, right? So that means that if you kind of draw a line on your complex plane, there's always going to be just finitely many roots on the right half of that. Okay. Now, this gives us hope that we can do a model reduction, and we can use those techniques which was developed by George's group. But indeed, we have to be very careful about it because we have many roots to deal with. Okay, and I kind of exchangeably use these roots sometimes, roots and eigenvalues. But as a matter of fact, it turns out that they are the eigenvalues of this linear operator. Okay, so this A sun star, which is also kind of a mathematical notation why we have to have the sun and star here. I'm probably not going to get into that today. Okay, so at least at the linear level, what we can do is we can actually dissect this system and start to basically project the system to the linear subspaces, right? Those invariant subspaces, those kind of trivial SSMs, right? Those planes. And then you can actually construct the dynamics as a sum of these plus some error. Okay? The only thing you have to be careful is that now your eigenvectors are going to be something more complex than we used to have before. And also the projection is going to be a little bit more complex what we had to do before. But in terms of principles, it's the same idea that we have a large dimensional system, and now actually infinite dimensional. We're going to come down to finite dimension. Okay? So if you calculate, for example, the right eigenvector, then you can see this is an exponential function. So it's going to contain that traditional eigenvector components. What we have is just a vector with numbers. But it's also going to have this function, because now we have to think about this tail in this case. Okay? And you can also calculate the adjoint operator, and you can calculate the solution for that. There is quite some algebra here, but what I'm trying to illustrate that this is actually doable. Okay, so there is a same way as we do it for ODEs, we can do it for DDEs, and as a matter of fact, at the end we just need to do some algebra to calculate these finite dimensional parts of the vector. Okay, I'm going to skip this part now, and I start to finally show you something about the SSMs. Okay, so let's try to look at the simplest possible case. We have one real eigenvalue. Okay, it's negative in this case, so this is a stable system. And we try to project the dynamics into that single direction. Okay, so using the same mechanism as before, you can build up this so-called spectral submanifold. Okay, and it looks exactly the same as you have seen today a couple of times. The only difference is that now these coefficients, they all become functions. Okay, so they kind of, some animals which are living some higher dimensional state space, yet the concept of having a lower dimensional manifold and my trajectories are going there and it's driving our dynamics is still maintained. Okay, as a matter of fact, the very first one of these is actually going to be your eigenvector itself. Okay, and then the benefit is that you got just one single nonlinear differential equation, right? So it's a one-dimensional reduction of your system. This is nonlinear, and you should be able to actually analyze the system, whatever you want to do with this, right? So this is a huge reduction. We went from infinite dimension to finite dimension. Okay? So actually, just to show you what I'm plotting here, I'm basically showing you the manifold such that I took away that linear dimension, so it's easier to kind of see how the manifold curves. Okay? So this sounds great, but I think the first question George asked, like, is this thing exist, right? So when does it exist? Are they smooth? These questions have to be generalized for time delay systems. In particular, that there are these resonance conditions. When we go through this algebra, you remember there used to be some kind of matrices which we have to invert. And in this case, that's not different. Right now, we have this operator which we should be able to actually check whether there are any resonance between the eigenvalues. And if you think about it, I can't do it anymore by hand. I have infinitely many eigenvalues. So what I should do is that I should take this red eigenvalue and I check it with every other eigenvalue's real part whether I have some kind of resonance, right? That would take a very long time. At least infinity is very huge. So how do you do this? And then luckily, George and his students came up with this idea is that, well, maybe we can have a sufficient condition. okay? And this is kind of neat because they said, well, let's just measure the real part of this dominant eigenvalue. And then let's take the same distance and measure it twice, okay? And if there are no eigenvalues on the right of that, then I can do this up to second order in power, okay? If there is no eigenvalues up to 3 times of that, then I can do it up to third order in power. So actually, this is a sufficient condition, but this is checkable, right? It's very easy to check. I just check my eigenvalue, and it's dominant in this sense, then I should be able to do this, right? So that was a big relief, right? Because if this is not true, then of course anything we calculate would have no ground at all, okay? So luckily, this is still grounded on the same theory. The only difference is that now it has to be extended into infinite dimensions, okay? So again, the message is these exist the same way for infinite dimensional system as they existed for finite dimensional system, but there is an additional kind of complexity here, which is coming due to this infinite dimensional nature of the system. You can do the same thing, for example, if you have a complex conjugate root. So most of the problems you have seen today, and those videos were shown by the other speakers, were systems which had oscillatory motion, right? And then, so it's important that it's possible to do it in that case as well. And indeed, in that case, your reduced order dynamics becomes 2-dimensional, right? But still, 2 is much less than infinity, right? At least in my math. So it's a huge reduction what you can do with the system. And again, it gets algebraically more complex, but the linear part is related to those eigenvectors. And the reduced dynamics can be very, very simple. As a matter of fact, you can get rid of many of these terms, and you can get this normal form or Stewart-Landau equation, which I actually checked that who Stewart was. He was a British scientist, actually passed away only 3 years ago at the age of 93. So I mean, sometimes you're using these equations, we don't even know who is behind. So the bottom line is we are able to actually now characterize the dynamics in 2 dimensions. Okay? And from the control perspective, this has a huge importance because things can happen in this 2-dimensional space which is not going to happen in 1 dimension. Okay? So one of the most important things is that, as you see now here, is a very kind of trivial looking solution. The solution comes over the spectral submanifold, and it's going to go along it, right? So if you would shoot it with some other numerical techniques, well, maybe not as elegantly as SSMs, but you should be able to recover these dynamics, right? Maybe you need a lot of Fourier components to do that, but it would be actually possible, okay? However, there is the possibility is that now we can have this unstable limit cycle living on this surface, and that indeed changes the problem. And this is what we have seen in case of the traffic jams, that indeed there was an unstable limit cycle. So now it's important what happens on this manifold, right? It's not just I go to the manifold and then on the manifold I go to my equilibrium, but indeed, depending on the initial conditions, I can actually see either a decaying solution or I can see something which eventually grows into a congestion wave. Okay? So because of this simplification, actually we can rewrite it into a simplified form again. And then you can figure out when this limit cycle actually exists, right? So if you, for example, do control design, you can choose your controller that it doesn't exist, right? As a control design, we actually want to get rid of it, right? So that's kind of our goal to do it. And we can calculate the amplitude. We can also calculate the angular frequency. And even though we have an infinite dimensional state space and life is complicated and so on, we can still map it back to the original space, right? Because after all, that's what we are going to measure. So if you calculate your original oscillations, then you're actually going to get some approximation of this periodic orbit. And you can see that this is kind of an interesting series because it's somewhat a mixture of a Taylor series and a Fourier series. You see these kind of higher order terms in terms of the amplitude, this rho. but you also see higher order terms in terms of the frequency, right? The double frequency and the triple frequency also shows up. Okay? So this gives us a very nice representation of the system. And this can actually capture dynamics, which is much, much accurate than if you try to shoot it with some linear techniques, right? So this you cannot get from linear techniques. And that would be really something where if you use these SSMs and allow you to identify the system, and as I will demo in a few minutes, just to keep you here maybe for another 10 minutes, I will show you that actually you can use it for control design. Okay? Maybe before we go into that, any questions before we move on to that? It's getting really late, right? Okay, let me speed up. So maybe I will just show you one simple example. So this is always good to have like a very simple thing. So in this case, it's a scalar example, right? It's nonlinear. It has time delay in it. And it's so nice that actually you can calculate analytically what is the spectral submanifold. You can also calculate what is the reduced order dynamics. Okay, so this is this simple, right? So you can get it on the nonlinear level, which is quite amazing. And you can indeed also study, when do you have, for example, resonances. As a matter of fact, this system has two resonances. One of them is when the two eigenvalues are the same. It turns out that in this case, there are only two real eigenvalues, so it's very simple. In this case, we can actually check that resonance condition. And then there's another one when there's a 1 to 3 resonance, right? So you kind of have to take care of those. And you can actually go around them. So there are ways that you, if you meet them, then you can actually choose your nonlinear form slightly differently, and actually it's still doable. But you can actually identify them, right? So I think every technique has something which we have to be careful about. And in case of SSMs, this is the resonance. If you do control barrier functions, then you know that wherever the LGH goes to 0, that's where your problem starts to arise, right? So there is no like silver bullet for everything. Okay, so we can actually do this at the real eigenvalue, and actually we can also do the same calculation for the complex conjugate roots, and you can see again that now the spectral submanifold starts to get a little more complex, right? But the reduced order dynamics is still beautifully simple, okay? And this actually can reproduce that in this system, for certain parameters, we do have an unstable limit cycle, okay? Again, as someone working on dynamical systems, this is something fascinating and interesting and nice to understand the dynamics, and we can actually capture it with SSM with very high accuracy, right? As a control engineers, this is what we want to get rid of, right? Because this is really bad for control design, because your linear design is telling you everything is fine. This is a perfect system, yet you hit a perturbation, and suddenly a catastrophe happens, okay? So in the engineering perspective, this is very important to actually avoid this. Okay, and actually we did that for the example. So here, as I mentioned, this is kind of more complex, so I'm not going to go through all these details. But basically what we did was we said, well, we need to have a model for the human. You can actually learn it from data, or you can set up a very simple model, like, for example, what we did here. And indeed, again, I kind of, as I said before, we kind of make it dependent on the velocity difference, right? So this was what the question was about, where is the h dot? It's actually there. And then you can also, you have to do a Taylor expansion, right? After all, there is approximation up to what order you want. And then, interestingly, you can also sum up with your control design in a very similar form, right? You can say, I just set it up as a Taylor expansion, and my job is to find these different gains in this case. Okay? So if you do this, your job is to make sure that that unstable limit cycle doesn't exist, right? So you can actually choose these betas such that the reduced order dynamics is simpler, okay? So if you do this, for example, you set up the SSM, you check your reduced dynamics, again you go to this complex plane, then you learn that what we need to do is that this particular real part of one of the components has to be actually negative. And if that's negative, then you get two benefits. One, you don't have the unstable limit cycle, right? So safety sense, you're not going to die. That's great. Okay, it's already a benefit. Second thing is, if you actually solve this nonlinear equation, which actually can be solved, right? This is so simple analytically, then you actually can show that this actually decays faster than the linear counterpart. Okay? So you take the nonlinearities, which in some sense used to be your enemies because it gave you a difficult control problem to design, and you make it your friends because by designing a right nonlinear controller, actually you can make the system to attract faster. Okay? So you can write a very simple optimization in this case that I want to have all these coefficients to be close to 0, except the one which I really care about, which I want to have negative. And if I show you how does it look like at the end, you basically see that if you only use a linear control design, then typically the system decays really slow. But once I kind of make sure that I design also the nonlinear terms in the controller, then it actually decays twice as fast. Okay, so that's an important thing, that you can do something beyond the linear design. Now, can I only do equilibria and periodic orbits? No. And then recently, actually, there was a publication in collaboration between George's group and Professor Stepan's group. And then they actually had a chaotic pendulum. As you can see, this is again back to the balancing problem, which I showed you at the beginning, right? So this robot is not doing very well, right? First of all, important to mention that in the back, there is this huge gas container. That has nothing to do with the experiment, okay? That was just left there by accident. But what you can see with this pendulum, which is in this case is a 2-degree of freedom system, is that it's shaking. So somehow it's not able to do that. And this is related to the fact of this is a digital controller, and actually the digital effects cause this shaking. But actually makes the motion chaotic, okay? Yet, even though it's chaotic, and now, of course, we need a higher dimensional subspace. So it's not 1 or 2, what I showed you before, but it's actually a 6-dimensional subspace. You can see that you can actually trace the trajectory and predict it very well. And maybe the static picture actually shows it a little better. So it's really a very nice prediction of a chaotic motion. And of course, they did much more on this. They did it check the distribution. So this is really a good prediction. It's not just looking good. But again, we went from an infinite dimensional state space down to 6 dimension, right, which is really manageable in dynamics and control. And then you can do predictions there, and you can also do control design there. Okay, so that's kind of the main message which I want to leave you with. And before I go, just one more thing. There's a true motivation, especially why I'm working on these type of problems, especially how is it related to traffic dynamics. And there is a interesting explanation of this, and I want to leave you with this. Unfortunately, the sequel is already ended, right? So Tom Cruise has been running for about 30 years. But then at the end, I think last year, he finished his quest. So this is about 20 years ago. And everyone just thought that, he's a secret agent who is saving the world. But actually, he was a well-trained researcher. So let me let him explain that.
Department of Transportation.
I've been there over 10 years now.
And what do you do at the DOT?
I study traffic patterns. You hit the brakes for a second, just tap them on the freeway. You can literally track the ripple effect of that action across a 200-mile stretch of road because traffic has a memory. It's amazing. It's like a living organism. Freshen that up for you, or is it vodka martini?
Yeah, thanks.
Ladies, do you?
So wait a little.
I've married. I would too.
So now you understand our true motivation doing the research. And with that, thank you very much. And I'm happy to answer any questions.
All right, we have time for some questions.
Now that we studied a system without delay, with delay, can this formulation be applied to the stochastic differential equations?
It can, but it's probably not the best person to answer to that.
There is a paper for SSMs for random dynamical systems. In this case, we assume the forcing is deterministic and bounded. This is a publication that we have. It's called, you can maybe hit up random SSMs, where we show the existence of SSMs for systems that have stochastic forcing, but the forcing should be uniformly bounded. But where we tested it on various realizations for plates and beams, and we verified that we were able to recover the power spectral density, where we reduced something of, let's say, 1,000 degrees of freedom to just 2D, where you can project the forcing. So we have seen these examples as well for such systems.
So maybe to add something, so one interesting thing, where is this time delay system actually sitting at? So what you really want to do, you want to use it straight to PDEs, right? As a matter of fact, many of the problems the previous speakers talked about, they were actually systems which you typically describe by PDEs, right? And then they looked at some gridded versions of that, or they looked at certain observables. And in some sense, time delay systems sit somewhere between ODEs and PDEs. And one of the reasons is because our spectrum is nice. So in this case, we have single eigenvalues, right? For PDEs, you actually might have lines on the complex plane. And then these kind of non-resonance conditions can become much more tricky. So actually, I think George has an example where he did it for a PDE, right? But in general, that's a very hard problem, right? So in some sense, DDEs sit somewhere between the ODEs and the PDEs in terms of difficulty.
Another question. So you use the DDE. Like, did you have to use any DDE solver in your formulation in any capacity?
So let me put it yes and no, right? So of course, the problems I showed you today, they were so simple that indeed we can actually compare it to the ground truths, right? So that's what we did actually. So we indeed did the reduction and we compared it to the true system, right? Having said that, the last example I showed in case of the chaotic pendulum, that actually did not have to solve the DDE anymore. It was simply from data. So what I didn't really talk is that the same way as it can be done for ODEs, SSM can be made data-based for DDEs as well. And in that case, you don't need a DDE solver. Essentially, you can just reconstruct it from data with some assumptions, as George said, right? We have to have an equilibrium around which we start to deal with. But otherwise, it's actually doable.
There, I want to add one thing that, so I was studying the delayed car following model for the IDM, and I'm gonna present that in IV next week. So
okay, well, I'm the program chair of IV.
We talked about
I think we're gonna meet.
Email. But the question there, the problem there I find out, or maybe for the lack of the experience in that sense, is that DD is the solver for the DD is very sensitive to the time step that you were that I was choosing. Okay, so in that case, it's hard to establish that what is my ground truth, and then is it the solver artifact that I'm seeing the difference in the limit cycle, or any other pattern that I'm seeing. So that's why I'm asking, like, if there is a issue with the solver, then is there any recommendations from you that to compare with a ground truth for in this case for a time delayed systems?
Okay, so maybe one practical recommendation is that keep your time step constant, okay? For example, DD23 gives you variable time steps. That's your enemy, not your friend, okay? May look things faster, but it's actually not giving necessarily the truth. On the other hand, I think, again, this is related to what I mentioned before. So these problems, typically in case of ODEs, are not so difficult, right? If you go to PDEs, your life becomes very difficult because you have to discretize both in space and time, right? And DDEs is, again, somewhere in the middle, right? So you already start to see some of these difficulties. And in that sense, it's a very nice kind of playground for us, mathematically as well, not just because of the importance, that, you know, this is something kind of exciting and it's interesting to work on.
Thank you.
All right, I think since this is the last session, maybe we should move on to the social events next. Let's thank our tutorial presenters. Big round of applause for a really nice tutorial. And yeah, enjoy the social events, and we'll continue tomorrow, 9 a.m., I think.